In this video, we're going to introduce the topic first order simultaneous differential equations. And what these are used to model, let's just have a look at this example question here. It says the population of foxes, x, and rabbits, y, on an island at time t are modelled by those simultaneous equations here. So the rate of change of foxes, dx by dt, is 0.1x plus 0.1y. So trying to make sense of this, it's saying the rate of change of population of foxes depends on two things. It depends on the current population of foxes and the current population of rabbits, which sort of makes sense because the more foxes there are, the more foxes are going to be born, and the more rabbits there are, the more food the foxes have. So the rate of change of fox population again depends on the current number of foxes and how much food the foxes have. The population of rabbits, the rate of change of the population of rabbits, negatively depends on foxes. So that sort of makes sense as well, because the more foxes there are, the more rabbits are going to get eaten. And the current population of rabbits, so the more rabbits there are, the more rabbits are going to be born. So that's what those two simultaneous equations are saying, and they're quite often used to model this predator-prey interaction. But what's not so useful about these models is it's the rate of change that we're given. So we need to know the population of foxes and the population of rabbits in order to work out the rate of change of the population of foxes. That's a lot of work. So it would be much easier if we just had a formula for the population of rabbits in terms of time and the population of foxes in terms of time. So the aim of such a question is to solve these differential equations and get a solution in the form x equals a function of time, i.e. that will allow us to see the population of foxes at any time, and y equals a different function of time. So we can see the population of foxes if we know the time, and we can see the population of rabbits if we know the time. So really what we're trying to do is decouple these equations to get x equals f of t, y equals g of t. So that's what we're going to do. So that's the purpose of this question. So I'm going to cut back this question a little bit, and I'm only going to look at the part that we're doing. So we'll concentrate on part one for now. So it says, show that d2x by dt squared minus 0.4 dx by dt plus 0.05x equals 0. Well, what we're going to do, we can see a d2x by dt squared, so we're going to differentiate this equation here with respect to t. So differentiate dx by dt, we get d2x by dt squared equals, and if we differentiate 0.1x, we get 0.1 dx by dt plus 0.1 dy by dt if we differentiate that. So what we've done, we've differentiated this first equation here with respect to t. But notice here we've got a dy by dt in. Well, actually, we can replace that, eliminate dy by dt, by just replacing it with this expression here. So let's do that. So this implies that d2x by dt squared equals 0.1 dx by dt plus 0.1, and let's replace that with minus 0.2x plus 0.3y. And notice in our target expression, there's no reference to y at all. It's all differentials of x with respect to t and x's. So we need rid of this y as well. And this is the same process you'll follow every time, because we can get rid of this y here by rearranging this top equation to make it say 0.3y equals. So let's do that. So since dx by dt equals 0.1x plus 0.1y, let's times it by 3. That means that 3 dx by dt equals 0.3x plus 0.3y, and rearranging it to say 0.3y equals, so we can replace this, we get 0.3y equals 3 dx by dt minus 0.3x. So now replacing that there, we get, going back to this line here and replacing the 0.3y, we get d2x by dt squared equals 0.1 dx by dt plus 0.1 minus 0.2x plus, and let's replace 0.3y with this expression here, 3 dx by dt minus 0.3x. Let's tidy that up a bit, which in turn implies that d2x by dt squared equals 0.1 dx by dt plus, or minus rather, 0.02 x plus 0.3 dx by dt minus 0.03 x. We're almost there. Let's gather everything up and taking it all over to the left hand side. So d2x by dt squared equals, we've got 0.4 dx by dt, and then minus 0.05x. Then finally, that means that d2x by dt squared minus 0.4 dx by dt plus 0.05x equals 0. And that should be our target expression there, which indeed it is. So we've got the answer. So we've showed what we need to show. So now the next part of the question says find the general solution for x. Now this relies on you being able to solve second order differential equations, because we can see that these simultaneous equations have reduced to solving a single second order differential equation. If you're a bit rusty on second order differential equations, or you haven't had a go at it yet, have a look at the tutorial videos I've done on second order differential equations. So some good examples there. So anyway, find the general solution for x. So the first thing we do when solving a second order differential equation is make the auxiliary function. So m squared minus 0.4m plus 0.05 equals 0, and solve that equation there. Which means that m equals, and what we can do, because it doesn't say show full working or detailed reasoning, we can just use the calculator solver. So we've got 1m squared minus 0.4m plus 0.05. We get that m equals 2 plus or minus I over 10. So equals 2 plus or minus I over 10. Or we can rewrite that as 0.2 plus or minus 0.1 I. So we know that when we've got a solution to the auxiliary equation of this form, alpha plus or minus beta I, we know the general form of the solution for that is e to the alpha t, a sine of beta t plus b cos of beta t. And that's just something you've got to learn. Again, a justification of that, why that solution takes that form, I've done in one of my previous tutorial videos. So if you want to see a proof of why, have a look at the previous video. So then that means our solution for x is equal to e to the power of 0.2t. Then we've got a sine, mustn't forget to put the constant, a sine of 0.1t plus b cos of 0.1t. And there's the general solution, so 4 marks. So next, we'll have to find the corresponding general solution for y. Well, we can nice and easily do that if we remind ourselves what the original equations were. Let's take a snapshot of those there. Just paste them down here, remind ourselves what they were, so those equations there. Well, I've got x here. What I can now do is find dx by dt. So I can differentiate that to get dx by dt. So dx by dt. And I'm going to use the product rule here. So I've got u equals e to the 0.2t, which means that u dash equals 0.2 e to the 0.2t. V equals a sine of 0.1t plus b cos of 0.1t. So v dash equals, and that becomes 0.1 a cos of 0.1t plus 0.1 and the differential of cos is minus sine, so we'll change that into a minus 0.1b sine of 0.1t, which means that dx by dt equals vu dash plus uv dash, which gives, so v is a sine of 0.1t plus b cos of 0.1t. So v times u dash, which is 0.2 e to the 0.2t, then plus uv dash, so plus e to the 0.2t, and v dash is 0.1a cos of 0.1t minus 0.1b sine of 0.1t. Let's now take out a factor of e to the 0.2t, so that equals e to the 0.2t, open bracket, and remember everything here is times by 0.2 as well, so 0.2a sine of 0.1t plus 0.2b cos of 0.1t, and strictly speaking I should put brackets around this just to show where the sine, which terms the sine function is applied to. I know I haven't above, but whenever I try to remember, I will put brackets around those. Okay, then plus 0.1a cos of 0.1t minus 0.1b sine of 0.1t. So now we've got that, we're going to use this equation here, because we know what dx by dt is now, just in terms of t. We know what x is, just in terms of t, so we can then sub that in there and rearrange it to say y equals. So that means that dx by dt, which is that, e to the 0.2t, 0.2 a sine of 0.1t, plus 0.2b cos of 0.1t, plus 0.1a cos of 0.1t, minus 0.1b sine of 0.1t. Then it's equals 0.1x, so 0.1, and we're told that x, before we've got the solution just here at the top of the screen, there's x, 0.1 of e to the 0.2t, a sine 0.1t plus b cos 0.1t, close bracket, plus 0.1y. So let's take all of these terms to the other side to get 0.1y equals. So 0.1y equals, we've got e to the 0.2t, and we're just going to write this out again. So I'll speed things up by just copying that. There it is there. Close bracket. Then take, because what we're doing, we're taking this term now to the other side. So take this one here. Take away that there. Which implies, and let's times everything on both sides by 10 now. So all these 0.1s are going to go. So we'll get y equals, and if we times each of these by 10, that 0.2 becomes 2, 0.2 becomes 2, so we get e to the 0.2t, and that becomes 2a sine 0.1t plus 2b cos 0.1t plus a cos of 0.1t minus b sine 0.1t minus e to the 0.2t a sine of 0.1t plus b cos of 0.1t. Almost there. We can take out this factor of e to the 0.2t in all terms. So y equals e to the 0.2t. Quite a lot of intense algebra here, but that's this topic for you. Right, so let's gather up all the a sine 0.1t. So I've got 2a sine of 0.1t there. Now I've got a sine of 0.1t there, which I'm subtracting. So that just becomes a sine of 0.12t. A sine of 0.1t rather. So that's, I'll put a little mark under them. There, done that one there. Right, let's have a look at the b cos of 0.1t's now. So I can see I've got one there, and I'm taking one there. So take, so I've got two there, take one, so that becomes positive b cos 0.1t. Now let's have a look at the a cos of 0.1t's. I've only got one there. A cos of 0.1t. Take b sine of 0.1t. I should close that bracket there. Okay, so there's the solution. And you'll find that this is what you do every time. You get your solution for x. You differentiate it like I have here. Then sub it into this equation here, which you can then rearrange. So sub it in there. We've got x as well that we can sub in there. That is in terms of t. So then you end up with an expression for y purely in terms of t, like we have here. So the next part tells us initially there are x0 foxes and y0 rabbits. So when t equals 0, x equals x0, y equals y0, find the particular solutions. So let's sub that in. Let's sub t equals 0 in for x. So t equals 0 and x equals x0. And let's look at our solution for x, which is up here. There it is there. So I've got my solution for x, which I'm going to copy and paste just down the bottom. There it is there. So I get x0 equals, so e to the 0.2t when t is 0 is just 1. And sine of 0 is nothing, so that disappears. Plus b, so a sine of 0 disappears, plus b. Which means that we get b equals x0. Let's do the same thing for y now. So let t equal 0, y equal y0, which means that y, which is y0, equals, so e to the 0 is just 1, then all the signs disappear because we're finding sine of 0, so it's just b cos of 0.1 times 0 is b, plus a, and we know the value of b from above, there it is there, equals x0 plus a. So that implies that a equals y0 minus x0. Therefore, if we conclude, so we've got x equals e to the 0.2t, and we know that a is y0 minus x0, so y0 minus x0 sine of 0.1t plus, and we know b is x0, so x0 cos of 0.1t. We know y equals, so our solution for y is just here. Let's zoom out a bit. Keep that at the top of the screen. So y equals e to the 0.2t, and a was y0 minus x0, so it's y0 minus x0 sine of 0.1t plus b, which is x naught cos of 0.1t plus y naught minus x naught cos of 0.1t minus x naught sine of 0.1t. And now gathering up all the sine of 0.1t terms, so I can see that here's the sine 0.1t terms here, and here's one here. So I gather them all up into one neat bundle. I get that that's equal to e to the 0.2t. And we've got y minus x naught as the coefficient. So y minus 2x naught sine of 0.1t. And the unhighlighted terms in cos t, I've got x naught plus y naught minus x naught, which is just y naught as the coefficient, plus y naught cos of 0.1t. And there's our answers. So there's one solution for y, and there's the other solution for x. So y equals that, x equals that, and that's the question done. Well, let's just take a time to reflect on what we've just achieved here. So if we go back to the original question, we started off with two differential equations in x and y relating the rate of change of population of foxes to the population of foxes and rabbits, and the rate of change of the population of rabbits to foxes and rabbits. Now, that's a really inconvenient form to have it in, because you've got to know information about the population at any one time, so of both species. So what we really want to do here is decouple these and actually find an expression for the population of foxes and rabbits based on time. Well, that's what we've achieved here. Gone all the way through the question, and we're left with x equals in terms of time and y equals in terms of time. And that's really the purpose of this method, to completely separate those differential equations and derive a formula for x and y in terms of just t. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to alevelmathsrevision.com.